So the plot for average error sort of looks like this. So this is average error. Remember that in average error we remove the sign, so they all, everything looks positive. Okay, this has a negative bias and this has a positive bias.
What is that second to the last model?
Oh, this one?
Yeah.
This is the power model. Sorry about that.
Oh.
Power model. And this is S shape. Power model was proposed for hardware by someone, and mostly it doesn't work well, but because it has a different expression, so we thought that we should try it. And now one interesting observation is that, notice that this has a negative bias, this has a positive bias. So does it suggest you something?
Underestimates.
Yeah, so this one underestimates, this one overestimates. So, so some people they came up with a clever idea. This one overestimates and this one underestimates. Maybe I could combine the two. So there are some approaches that people have proposed which will do a linear combination of the models. Take overestimation, underestimation, and somehow do some kind of combination. And that probably might give you a better result. There are some papers based on linear combination of models, if you can look them up in the literature. Any questions or comments? Okay, now how do you use a software reliability growth model? A software reliability growth model can be used in two different ways. I was at, as I was mentioning, ISSRE this last few days in San Jose, and there were quite a few companies. For example, somebody who makes a medical device, I think heart for pacemaker or something. So their software has to be really reliable. So they are using software reliability techniques, and there are many other companies that use software reliability techniques. Most companies, they do software reliability growth modeling either formally or informally. Some people use it informally. They look at the trend, and when the trend goes below some acceptable limit, they think they have done enough testing. How do you use NSRGM? So there are two different ways. So you can use it for preliminary planning. And so you get some initial estimates of parameters. And then, so let us say that there's some software and we have some rough idea of the size of the software and some of the static metrics. So based on, if you can estimate beta 0 and beta 1 for the exponential model, you can calculate how long it will take for the failure intensity to go below some threshold value. And you can assemble your team and you can tell your manager that this is how many people you need and how much they should work on testing. Other is during testing. So you have actually been doing some testing and you have collected some data. And so based on this data that you have collected, you can now make a better prediction of when you are going to be able to achieve your reliability target. So let's look at first this initial planning. An example. Incidentally, I should mention that software reliability growth models, they assume that the software is not evolving. So you have already done your implemented the software and you are testing it. So it is assumed that there is no evolution. And things get interesting when there is software evolution. So we have been doing some work on impact of software evolution specifically for vulnerabilities. But I think people should think about looking at the effect of evolution on software reliability engineering, which is the software reliability growth modeling. That has not yet been adequately examined by researchers. So, okay, so let's look at an example. Let us assume that you estimate initial defect density to be 25 per 1,000 lines of code. And let's assume you have 10,000 lines of C code. C is still a fairly popular programming language, C or C++. And let us say you have a computer, and I happen to have an older number here. So 70 million instructions per second. Now this is an old number. These days, let's see. So you guys have taken the course on computer architecture, right? So what is the current, the latest processors? How fast do they compute? So you have what? 2-3 gigahertz, 3-4 gigahertz clock frequency. So and then these days, the number of instructions executed per clock period, it can be close to 1 because of pipelining. So if there's enough pipelining, so you can get a modern processor much faster than this. But anyway, this is an example. And let us assume that the fault exposure ratio we take that to be average, which is 4 multiplied by 10 raised to minus 7. So we need to, okay, so find testing time for defect density to reach 2.5 per 1,000 lines of code. So right now it is 25 per 1,000 lines of code. So how much testing you need to do? So your defect density, estimated defect density, is going to drop down to 2.5 per 1,000 lines of code. Here's the question. So how would you do that? Okay, here's the procedure. First you will find beta 0 and beta 1, and then plug things into the formula. So, okay, let's calculate beta 0 and beta 1 here. Okay, what about the beta 0? Okay, 25 per 1,000 lines of code defects, and you have 10,000 lines of code. So 25 by 10. So your initial estimate is 250 defects. And beta 1 is equal to K divided by SQ 1 by R, and it is given by 4 multiplied by 10 raised to minus 7 divided by.
Why, or how did you get beta 0 again? Times the initial defect density?
Yeah, beta 0 is the total number of defects.
Okay.
The initial number of defects. So defect density, which is measured in number of faults per 1,000 lines of code,
Okay.
multiplied by the number of 1,000 lines.
Okay.
So you have to make sure that whenever you multiply or divide, the units have to match. So if it is per 1,000 lines, then you have to put the number of 1,000 lines of code, right?
Yeah.
So otherwise, your numbers would be off by a factor of 1,000. Okay, and S is 10,000 lines multiplied by Q, and so we can look this up. So there's a table given in the book that I have made available on the course website on software reliability. It's called what's it called, Reliability Handbook or something. So what's that?
Software reliability.
Some software something. Software reliability handbook or
Something close to that.
yeah, it's something close to it, but it's on our website. And usually I would not be able to provide such a well-written book publicly, because it was actually a study done. It was compiled for a government organization, and according to laws, that makes it public domain. So I have made it available. Incidentally, I met the author, Neufelder, in ISRI, and she's actually now a software consultant. So she gives seminars, and she actually consults with defense organizations. So she talks about some of these things, and she has her own software, and using her software you can estimate defect density, how much time you should spend to test, basically some of these type of things. Okay, and so you can look up the value of Q, and it will come out to be 2.5. So let us assume that going from C to some PC, whatever architecture it is, you get 2.5 object instructions per source instruction. And let me put in the number for the processor, which is 70 multiplied by 10 raised to 6.
For the assignment, can we assume that Q, 2.5?
This Q?
Yeah.
Yeah, we have taken this Q to be 2.5. So we basically looked it up in a table.
Okay.
So there's a table given in Neufelder's book.
And on the assignment, we should look it up in that table?
Yeah.
Okay.
So yeah, so so she has given a table that for this high-level language, this is the object, the number of object instructions, and right. So yeah, that's what you need to do for the assignment, and that comes out to be this per second. Remember, beta 1 you are going to multiply it by time, so the units of beta 1 is per unit time. So we got beta 0 and beta 1, and next is how much you should test to decrease the defect density. So basically what we are saying is that we want n at some time t1 divided by n at time 0 equal to